Hello everyone, this is going to be a quick announcement and explanation on NASA's InSight Mars lander. I will go more into detail about every individual part of the mission and every individual part of the lander later on during its flight time. So this is going to be a brief overview and introduction into the flight profile and mission of InSight. First of all, InSight is scheduled to launch today in a few hours, which makes for two interesting spaceflight events today, but only one of them really needs much deeper explanation. The SpaceX Dragon capsule CRS-14 is also scheduled to depart the ISS today. Now, both are funnily somewhat weather-dependent events. However, even though there has been some fog around the launch site, InSight is still scheduled to launch today from Vandenberg Air Force Base on an Atlas V rocket, with a 2-hour launch window starting at 11 o'clock GMT, and the Dragon capsule release scheduled soon after that launch. Of course, we are currently in a relatively ideal launch window towards Mars. It's not only in the middle of a transfer window, but also specifically one where you arrive relatively close to Mars periapsis, which actually makes a good bit of difference, especially when you aerobrake at Mars, so you don't have to completely boost up that orbit to its apoapsis, but you can arrive at the periapsis with a relatively low-powered drive, and the quote-unquote second burn in the theoretical standard Hohmann transfer will basically be done completely by aerobraking. The flight path is nothing incredibly complicated or fancy. It's relatively aggressive. It takes a relatively good launch window. It will take only 6.5 months to reach Mars. Most of the Delta V, therefore, will be delivered by the Atlas V launcher itself. The lander's own propulsion will only do a few corrections and minor boosts. Once at Mars, InSight will enter the atmosphere at a little over 6 kilometers per second while encapsulated in its heat shield, which is controllable for basically blunt body gliding, where you have a very, very low lift-to-drag ratio, obviously, because it is a typical blunt heat-shielded re-entry capsule. But it hits the atmosphere slightly oblique, and by turning it around you can somewhat control your flight path and aim your landing to actually land precisely at your landing site and not somewhere. Like most Mars landers, InSight will use a parachute to slow down its descent, but due to Mars' thin atmosphere it can't really just land on the parachute. Instead, it drops out of it. It leaves the entire heat shield and aerodynamics body and transport spacecraft and the parachute behind and drops in what's basically a free fall before then doing a powered landing on Mars. It just needs much less Delta V for that because the parachute has already slowed it down, but it's not really a landing parachute. Then once landed, InSight is a stationary lander. However, for a stationary lander it's a relatively complicated one. So it's not a rover, it's not going to explore all over Mars, but it has quite a few instruments on board. Some of them are so complicated that they basically need a small robotic arm on board to install those. These instruments are also where the most collaboration happened between NASA and their jet propulsion laboratories, who built the spacecraft itself and a few experiments, as well as many universities and some other space agencies, as well as ESA and some European institutes, including the German DLR and the Institute for Spaceflight Systems at my university, who contributed to the mole experiment, which is one of the more unique things InSight is going to do. Now, InSight is going to measure a lot of data. It has some cameras on board, some temperature sensors, a few weather sensors, as well as what's basically a precision navigation unit, which together with other data will tell us more about Mars' actual rotational parameters, like how its rotational axis tilts and changes and slightly tumbles over time. All planets have that, but so far we only really have precise data about it for Earth. But InSight's more unique key mission is of course to study the inside of Mars using several instruments that let us make conclusions about this. Now, it's not going to actually drill very deep into Mars, but it will have a lot of sensors that let us make conclusions about Mars inside from other data. It will of course measure seismic data, as in basically small Mars quakes or earthquakes on Mars. And if you measure different effects of these, as well as know where they originate, you can measure how fast different parts of that earthquake's waves propagate through Mars' surface. That's basically going into seismology and well, basically mechanics. If you have a mechanical wave going through a material or through a planet's crust, you have longitudinal and latitudinal waves that basically compress and stretch the surface, and ones that basically shear it, and those propagate at different speeds and through different parts. And without going too much into detail, that can tell you a lot about the deeper insides of a planet without actually having to drill all the way down. And InSight is not really going to drill that deep into the planet. Now, the interesting drill on InSight, the mole experiment, is actually going to do something else. It is only going to drill down a few meters, which is pretty deep for another planet so far. But of course, it's not really going to study the core of Mars itself. Instead, it is going to measure how the ground changes as you go down, different properties of the Martian soil, and most importantly, temperature. And that can tell us a lot. As you go down, the temperature changes, and it also reacts to temperature changes at the surface, which InSight also measures, with a delay. And that delay can tell you about things like the thermal conductivity and thermal capacity of Martian soil, which together with the thermal gradient, or the temperature difference over a certain depth, can tell you about the thermal flux. And you can basically do a rough extrapolation as to how warm Mars is on the inside at the core. We know that Mars has no longer a molten core, and that it no longer has a magnetic field, which is also part of why it doesn't have a very dense atmosphere anymore. Again, I won't get too much into detail about planetology. It is a very complicated subject. There are a lot of factors contributing to each other and acting on the same parameters, so what actually causes what can sometimes end up being almost a philosophical debate, especially if you end up discussing things like the possibility of life once having existed on Mars with sometimes slightly ideological people. But back to the actual science, we know that among other factors, Mars cooled down faster than Earth because it was smaller. This is roughly speaking a square function, so approximately if you have a planet half the size, it will cool down 4 times as fast, because under each bit of surface area you have less material, so you have less thermal capacity, less stuff that needs to cool down, and at the same time you have also less distance or less way through which that heat must be transferred. We know that Earth is still mostly molten with a thin solid crust, and we know that with information like the thermal capacity or thermal conductivity of rock and soil, we can roughly estimate how fast a planet is going to cool down. Now, of course, depending on different models, these estimates go apart a lot, and for Earth we can estimate that to take some 10 to 30 billion years or something. Mars is about half the diameter of Earth. It's also further away from the Sun and has some other properties that should speed that cooling down up. But of course, with looking at the actual thermal properties of Mars, its actual estimated core temperature at the moment, and its seismic and geological properties, we can get a much more detailed idea of the history of Mars, which is interesting for many reasons. All of them equally valid, but of course the most spectacular one is that it brings us closer to understanding whether or not there might have once been microbial life on Mars, whether or not Mars has been habitable for a long enough time, hypothetically, and maybe even what the future of our planet might look like. Then, of course, apart from the actual science instruments, InSight has some slightly less serious, more for fun, but still quite interesting and important for public outreach payloads on board. including 2 silicon chips carrying lots and lots of names of basically random people on Earth who signed up for that on NASA's website, including my own, which of course isn't that amazing, but I still think it's pretty cool. Of course, they basically included everyone who signed up, so I and a million other people have their names etched on a microchip that will soon land on Mars, and at the same time we got that little boarding pass image to print out. And of course, if you go to spaceflight forums or Facebook pages related to spaceflight, you'll find long threads of people posting their boarding passes. The reason they were 2 chips is mainly that the mission was delayed once, and so they extended that sign-off period. So after the initial period closed and they etched a lot of names onto a microchip, they then noticed they had to delay the mission, and they let more people sign up their names and they etched them onto a second microchip, and so now they have 2 microchips on the lander. I still remember I signed up in 2016 for the original launch window, and I'm not entirely sure about the numbers, but I think it should be around 1.6 million overall names. So that's pretty cool. We basically got our small Mars colony there. So let's hope for the best for today's launch, and let's hope for a lot of interesting scientific discoveries about the inside and history of Mars, and a successful full-depth deployment of the mole hammer drill thingy. Of course, if you have any questions about InSight or spaceflight in general, I'm always open for requests, and as always, thanks for watching.